Volcanoes can explode even when no lava is visible. A sudden blast of steam and ash lifts straight up, powered by trapped water turning violent. This happens in fractions of a second. Pressure crosses a tipping point, rock fails, liquid flashes to vapor and hurls the plume skyward. Don't look for glowing rivers to judge danger. Steam-driven blasts are often gray and cold-looking, yet they carry real force. Safe distance matters. Closed rims can be lethal because ballistic rocks and scalding ash surge outward faster than you can run. Today, we'll decode the explosive physics of steam inside volcanoes, how heat, water, and confinement combine to create sudden eruptions. The recipe is simple: water plus heat plus a trap equals pressure. Enough pressure, and you get a steam blast. Spectacular lava isn't the only hazard. A dull gray crater with steady steam can be far more dangerous, with little warning. Think of a whizzing kettle. When vapor has no easy escape, pressure builds until the spout screams. Or a shaken soda. Release the cap and the fluid flashes. Gas expands fast, pushing liquid out explosively. We'll tour the inside of a volcano, see water become steam, follow the chain to a blast, compare types, and finish with safety. Beneath the crater lies a maze of fractures, hot rock, and groundwater. Together they form a hydrothermal engine. Rain and snowmelt seep downward through soil and cracks, recharging underground reservoirs around the volcano. Fractures act like pipes, channeling water through hot rock. The pathways can connect deep heat to shallow traps. As water nears hot intrusions, it absorbs energy. Convection starts, bubbles form, and the system stores thermal power. If a cap of clay-altered rock seals a cavity, fluids can't vent freely. Pressure begins to rise inside the pocket. Altered rock is weak. Microcracks and bedding planes become future failure surfaces when stress finally exceeds strength. Persistent fumaroles are the system breathing. They release gas and steam, but they don't guarantee safety nearby. The water table sits below the crater. Its position matters. Shallow water amplifies interaction with heat. Add heat faster than pressure can be relieved, and overpressure climbs. The system inches toward a threshold. In short recharge, heat, trap, pressurize. A simple loop, but one capable of sudden, dramatic outcomes. Heating liquid water creates vapor bubbles. When bubbles grow and coalesce, steam begins to take over the space. A tiny volume of liquid produces a huge volume of steam. That expansion does mechanical work on its container. Saturated water boils at its limit. Superheated water holds extra energy, ready to flash explosively if pressure drops. If volume is locked, heat pushes pressure up instead. With nowhere to expand, the system grows dangerously tense. Rock is porous like a sponge. Fluids in pores and fractures can be squeezed, jetted, or suddenly released. Break the seal and pressure collapses. Superheated liquid flashes to vapor in an instant, driving an explosive transition. The energy comes from hot rock and sometimes shallow magma. They're constant burners feeding the hydrothermal circuit. Small signals can simmer for hours, but the decisive failure and flash can unfold in milliseconds. Steam doesn't need to ignite anything. Its power is pressure and expansion enough to fracture rock and launch debris. Heat loads the water, confinement raises pressure, and rapid flashing does the damage. That's the physics in a nutshell. The chain is heat, trap, overpressure, failure, flashing, blast. Miss one link, and the eruption may never happen. When stress outruns strength, a crack races across the cap. A tiny opening can change everything. Pressure relief at the vent reduces boiling point. Liquid flashes, flow accelerates, and the system destabilizes further. Rapid vapor expansion hammers the cavity walls, propelling gases, ash, and fragments into a rising jet. The jet is mostly steam but carries ash and rock. Ballistic clasts arc outward and land far beyond the vent. Sometimes a dilute, ground-hugging cloud surges outward, scalding and abrasive even without glowing lava. Buoyancy lifts the column upward. White steam turns gray as ash mixes, and the plume entrains air. Danger is highest near the vent, but not only there. Projectiles and surges can cross well-marked trails. Eruptions come in flavors: phreatic, phreatomagnetic, and magmatic. Each has different signals and hazards. Phreatic blasts are steam-driven, often sudden, with fine ash and altered rock fragments. No fresh magma required. Mix magma with external water and fragmentation intensifies. Steam and molten fragments explode together. Magmatic eruptions are powered by gases in magma. They often show longer precursors and produce true juvenile material. Precursors vary. Phreatic events may show weak, brief signals. Magmatic unrest tends to leave stronger footprints. A calm-looking crater can be high risk. Clear air and gray rock don't mean safe conditions. Follow official hazard codes and guides. They reflect the best available monitoring, updated as conditions shift. Know the type, know the risk profile. It shapes how fast things develop and what threatens visitors most. Mount Ontake, Japan, 2014. A tragic reminder that steam-driven blasts can strike hikers with little notice. It began like any other day: quiet vents, thin steam, steady footpaths along the ridge. Then a sudden column surge scoured. Ash and steam engulfed the route in seconds. Visibility collapsed to near zero. In ash whiteout, orientation and breathing both become difficult. Avoid crater rims, heat alerts, and seek shelter from projectiles. These choices save lives. Steam-driven blasts can offer only minutes or less of clues. That's why pre-planning matters. Whakaru White Island, New Zealand, 2019. A tourist destination within an active hydrothermal system. Tours approach the crater by sea, guided and briefed, yet always within a zone of change. Boardwalks cross steaming fields. Activity felt stable until it wasn't. A sudden steam ash blast erupted. Near-vent exposures turned perilous instantly. Access zones exist for a reason. Inner rings can become dangerous without dramatic visual warnings. Go with trained guides, use protective gear, and respect closures. Conditions can shift faster than plans. Scientists listen with many ears: seismometers, infrasound, gas sensors, GPS, and thermal cameras. Tiny quakes can signal fluid moving or rock cracking. They're one piece of a larger puzzle. Infrasound records low-frequency breaths of a volcano waves to deep for human hearing. Gas ratios change as pathways open and close. Chemistry hints at the engine's state. Thermal imaging reveals hot spots and changing heat flow, mapping where energy escapes. GPS and radar detect subtle bulges and sync surface responses to pressure underground. Correlating signals sharpens interpretation. When multiple streams agree, confidence rises. Agencies convert data into alert levels. They inform closures, advisories, and public guidance. Still, prediction has limits. Some blasts arrive with little warning despite careful watch. Check official updates before visiting. Conditions, access, and risks can change day to day. Start at the signboard. Today's level, routes, and weather matter more than yesterday's experience. Keep out of crater rims and depressions. They funnel gases and amplify near-vent hazards. Watch vent activity and wind direction. A small shift can push steam and ash straight toward you. Helmets, masks, sturdy shoes, water, and a simple first aid kit. Basic gear for unstable terrain. Know how to leave quickly. Favor lower ground and wide, open paths away from the vent. Stay with the guide and move as one. Clear spacing and steady pace reduce confusion. Water plus heat plus confinement builds pressure. When failure opens a path, flashing steam powers the blast. No lava is still dangerous, warnings can be short, and respecting zones protects everyone. Next, we'll listen to volcanoes, how infrasound helps detect change before our eyes do. Thanks for learning with us. For more clear, visual earth science, join us on the next episode.